Thanks very much. My name's John Leonard. I'm from MIT down the road, and it's a real delight to be here. David's talk was so beautiful. You know, I think the brain is such an inspiration, and so in my talk I might try to say a little bit about some attempts I've had to collaborate with neuroscientists in thinking about mapping and localization for robots. But there's so much I want to say, and I know I'm going to run out of time, but I'll definitely stop when it's time. I work on problems of mapping and localization, so how robots build maps and use those maps to navigate. And I do that in a variety of domains. I've done a lot with autonomous underwater vehicles. Shown up here on the left are some vehicles from an experiment we did about 10 years ago in the Mediterranean. I was in the ocean engineering department at MIT, and I was helped build an autonomous underwater vehicle that was commercialized with a local company, Bluefin Robotics, back in the 90s. By some former colleagues. I also was the team leader for the MIT DARPA Urban Challenge team in 2007. And this is our vehicle, Talos, shown here on the right. And in the middle is a video of a robot doing something called SLAM, Simultaneous Localization and Mapping. Who's heard of SLAM? So I've been sort of obsessed with the SLAM problem my whole life. And it's come really to the forefront today because of developments in things like self-driving cars and drones. But also, I think in neuroscience, the questions of spatial memory in the brain are really vital and important, and I'll try to touch upon that. So so the topics I'd like to talk about, I'm going to talk a lot about self-driving cars, what the challenges are, and then some perspectives on robot mapping and localization, and then time permitting at the end, a little glimpse of some recent work with one of my PhD students on object-based mapping. So I'm sure you've all seen some of the media coverage of driverless cars. And a person who's, well, actually two incredible visionaries, Jensen Huang and Elon Musk, have said things. I have such incredible respect for them. And I think they think on different timelines. Like a decade to me is just a year to them. But they've declared self-driving solved in March. And Elon Musk said, I view it as a solved problem, and compared autonomous cars with elevators that used to require operators, but now you just press a button. And just very respectfully, I disagree. And I think that driving exposes fundamental issues in intelligence and fundamental issues in how the brain works. And we might be a very long way away. And so I don't know if anyone saw John Markoff's article on Sunday about self-driving cars still need humans. Markoff is in Silicon Valley for the New York Times. He broke the Google car story. And he had this article this week, he said, so it's hopefully just, fair use academic, purposes, and saying that, Tesla said that the autopilot is probably better than a person right now. And maybe under good conditions in following lanes, yes, but a lot of it deals with dealing with the unexpected. Elon Musk also said that a year from now, it would be possible to summon your car from one side of the country to the other, which is just mind-blowing to me. And so I was quoted in the same article, and I said the issue of interacting with people inside and outside the car exposes real issues in artificial intelligence. And the ability to know if the driver's ready and if you're giving them enough notice to hand off back and forth is a really tricky question. So I want to try to tell you, just elaborate on this view that I have that in terms of approaches to autonomy, the interaction with the human is one of the most important parts, and it's one of the things we need to do a lot more work on. How do the human and machine interact? And so my experience in self-driving is very much framed by the DARPA Urban Challenge, which was a large effort. I had wonderful faculty colleagues, Seth Teller, Jonathan Howe, Amelia Fazoli at MIT, and we hadn't done one of these challenges before. It was for a $2 million prize. It was $2 million for first place, $1 million for second place, $500,000 for third place, nothing for fourth place. Remember that. And but we sought to create a perception-driven vehicle. So DARPA originally said the vehicle should be able to follow sparse maps, where waypoints might be as far as 100 meters apart. We didn't want our car to blindly follow a prior map and follow GPS. We wanted it to navigate. We wanted to do a form of SLAM, a form of local self-referencing and navigation. So our vehicle used a really aggressive motion planning algorithm, something called an ROT, a rapidly exploring random tree, that built a local map that moved with the vehicle, and we populated that data with that map, that representation with sensor data from a LiDAR, which David mentioned earlier, and with vision. And we had to deal with things like looking into the sun and dealing with shadows and whatnot. So our vehicle, my late colleague Seth refused to be limited by sort of ordinary computers. He wanted a really amazing computer, so we got a blade cluster with 40 cores donated to us. That may not seem like a lot today, but back then it required 3.5 kilowatts to power the blade cluster. We needed a 2 kilowatt air conditioner on the roof to cool it, and a 6 kilowatt generator to power it. And one of the important sensors was this Velodyne laser scanner. This is actually driving up Mass Ave from MIT to Harvard. So I use this all the time, and now I've driven up Mass Ave from MIT to Harvard. And we can see people and trees and buildings. It gives you 1 million data points a second. And this is what Google are better at than anyone in the world, is processing this data to detect cyclists, pedestrians, other vehicles, and predict their motions. But back in 2007, it was very challenging, and I think still challenging today, to really make sense of all this data, to have a sort of sense of spatial awareness. So to make a long story short, the DARPA challenge, Carnegie Mellon came in first, led by Chris Urmson, who's now the leader of the Google self-driving car project. Stanford came in second, led by Mike Montemerlo, who's one of their key people. Virginia Tech third, and we came in a very distant fourth place. And something that I like to show, I think it's important for us to talk about our failures. And so I like to play this video. Maybe you've seen it before, but we had a little interaction with Cornell about 5 hours into the 6-hour race.
Check in once again with the boss.
That's Carnegie Mellon, who won the race.
Racing.
And
Remember, they were the
to set this up, we had been trying to pass Cornell for about 4 or 5 minutes.
Behind Virginia Tech.
And they were stopping and starting and stopping and starting.
Well, there we go. Got a little issue.
Here's 26 Cornell.
Each car had a chase vehicle that could stop it in an
looks like
emergency.
The 79 is trying to pass and has passed the chase vehicle for Skynet, the 26 vehicle.
Wow.
And now he's going to, and Talos is going to pass.
Very aggressive. And
Whoa! Oh, we had our first collision. Crash in turn 1.
oh boy.
So crash in turn 1.
That is, that's a bold maneuver. MIT to try and pass. And I'm sure the
So if you're a Boston driver, you might argue if that's a bold maneuver. But one of the things we can do with a robot car is we can look inside the mental computer representation and see what did the car see, what did it try to do. And it turned out Cornell had about 5 bugs, we had about 5 bugs of varying complexity. And this is the view of the car, and this is the local map I mentioned. Our car's here, and this is the Cornell vehicle. Now with the laser scanner data, all you really see is a blob of points. And even though the road was really wide here, the map from DARPA had just a single lane. And so our car didn't think it could drive over here in the red region. And when I click start here, you'll see the motion planner here generating about 50 random paths a second. 10 times a second, it generates 50 paths, choosing the best amongst it. And even when we started to pass and the car started moving, it was slow enough that when the white circle flashes, we tried to do an emergency stop, but it was actually too late. And in fact, we had a bug in our emergency stop behavior, which turned the vehicle straight. And if we hadn't done that, we might not have even hit them. And so we weren't using vision. So we can see with our eyes, there's a car or in a robot race that has a big number on the back and license plate and taillights. Maybe today a deep learning visual algorithm would just eat that up and know that it's a car. But thinking about intent and behavior, and because we didn't classify it as a car, we didn't give it sort of a safe clearance in front. We were missing that sort of semantic understanding of the world. And further, you have to remember that these programs, these systems have lots of code. We wrote about 150,000 lines of code, C++ code, in about a year and a half. And a lot of it is now open source. And embedded in that code are hundreds of parameters, thresholds, things that get chosen. And our wonderfully gifted PhD student, who's now a tenured professor at Michigan, Ed Olson, he was doing the object tracking, and it had a threshold that said that an object needed to be moving at 5 miles per hour or greater, or say 3 meters a second, sorry, or greater, and to be called a car. And that may seem kind of stupid. Cars can move more slowly. But it turns out if something's moving, if you set your threshold too low, due to the aperture problem, as you're moving through the world, buildings and railings and things, you could think that they were cars and they were moving, because everything seems to move as you move through the world. And something we're very good at is using our ego motion to sort of make inference about the world and not get confused by it. And so, in short, we didn't have enough time to test. We didn't have enough time to integrate vision. But all systems have thresholds. If you're familiar with ROC curves, receiver operating characteristic curves, or precision recall curves, you have a trade-off between probability of detection and probability of false alarms. And how you get those thresholds right and how you choose, it's really a challenging issue. So for this incident, we actually traded our data logs with Cornell, and we wrote a journal article. It's a 30-page peer-review accident report about this and some other incidents that we had. But what even though we came in 4th place and we had these sort of embarrassing moments, we had some great PhD theses come out of this effort. And this is Albert Wang, who is off in California, had been working at Google. He created a vision-based lane following system that on the fly could use vision and LiDAR to try to follow roads. And occasionally we get confused and stuck, but we tried to navigate not blindly with GPS. So this was back in 2007. And if you asked me today, like back then, it's like, when will we have a driverless car that could drive you in Boston completely hands-off? You could go to sleep in the car. And I would say it'd be a very long way away. But we were all surprised in 2010 when John Markoff, who I mentioned earlier, broke the story of the Google self-driving car. And this was, it turned out that Sebastian Thrun, who's a real visionary in this field, had formed a sort of secret team at Google X, a core group of about 10 to 15 amazing people, Chris Urmson, Anthony Lewandowski, and others. And they had driven 140,000 miles by this point on California roads without, the public were sort of unsuspecting. And it was just a real watershed moment. And if you fast forward now, 5 years later, the amount of activity in this space is just simply stunning. And so you've all probably seen some of these just so impactful videos that Google have made. This one in the upper left was taking a blind person, Steve Mann, to a ride to Taco Bell and to get his dry cleaning. That was 2012. The video in the middle shows driving in Mountain View on city streets, and I had the pleasure of riding in 2014 in that system, and it's pretty amazing. And then more recently, their prototype vehicle, where they now, I think, have built over 50 of them, and are actually using a vehicle that has no steering wheel. And so, but I want to try to give a balanced view, and I want to try to connect what's happening in the media today with driverless cars with some fundamental research questions. And I think the Google car is an amazing project that might one day transform mobility, and maybe one day will be very soon. But I do think the technology is misunderstood and somewhat overhyped, and I think it's led people to say that self-driving is solved, and I respectfully disagree. And I'd say that just because it works for Google doesn't mean it works for everyone else. And specifically, Google used a very detailed prior map shown in the middle there. They map with their laser scanner down to sort of 10-centimeter accuracy the streets of Mountain View, and they use that to locate the car very accurately. And so, if let's see, so if you think about if you're not using a very precise prior map, then a system is sort of that's turned loose in the wild has to be able to sort of make sense of the world. And maybe that will work 99% of the time, but what about the other 1%? And what about the interaction with the human? So what I wanted to do now, and if there's any questions, let me know, is talk about some of the specific challenges for self-driving cars. And I must confess that I'm rather obsessed with this problem. And so I drive around Boston thinking about situations. Could a robot car handle this situation? Could a robot car handle that situation? So for about a month, a year and a half ago, I put a dash cam on my car and I collected Boston driving data. I live in Newton. Does anyone live in Newton? And this is actually a cell phone video, not a dash cam, of one of my son's friends in the front seat. And here's a left turn on something called Parker Street in Newton. And if you look to the right, you can see that there are cars as far as the eye can see, because they put in a new traffic light and created a big traffic congestion bottleneck. And if you look to the left, there's cars coming at a pretty high rate of speed, and there's a mailbox and a tree that's occluding things. And what you have to do, a robot car might just sit there and wait all day, so we don't want that. And so so what I had to do was wave at the person and sort of, pull out. And so the human interaction to do these things, here's another situation. This is on Coolidge Corner, driving out in Brookline, and I'll show this again in a second. There was a police officer, and even though the light's green, the police officer says stop, as well as changes to the road surface or snow. And I'll show a longer version of the police officer. Here's a flashing light. So what do you do about flashing lights? One police officer waving me through a red light, and then at the next intersection, it's the police officer stopping me at a green light. So if anyone here is a programmer, how do you write the code that says always stop at red lights unless there's a man on the side of the road who's waving you through it? Okay, and changes to the road surface. So this is the Harvard Bridge after it had been repaved. That would be pretty bad. And obviously snow, the Harvard Bridge covered with snow. And not to criticize the Google folks, they're amazing, but the precise maps that they make to locate the car provide a sort of robustness that they can predict the expected and then better deal with the unexpected. And with snow or leaves covering the ground, the road getting repaved, how do you do that? And then, of course, if you want to just use vision and not LiDAR, you have to deal with situations like this. So let me ask, what do you see in this picture? There's some green lights, there's a sun. Does anyone see the police officer standing here? You can just make out the shadows from his legs. And so he just gave me this tiny little wave, walked across, and he's waving pedestrians across the way, even though the light's green. So for me, for driverless cars, the big questions going forward, maintaining the maps that say like a Google approach uses, dealing with adverse weather, interacting with people, both inside and outside the car. And then what I really think we need is robustness. So getting to the perfection point on the ROC curve, where you get near perfect detection and very few false alarms. And so you might be familiar with what's called level 2, level 3, level 4 definitions of autonomy. So level 3 is a situation where the car might do 99% of the job, but you have to be ready to take over when necessary. And so for level 3 approaches, I think the big question is how can humans be trusted to take control? And humans are actually pretty bad at that. So if a system works 99% of the time, and then 1% of the time you have to suddenly take over in an emergency, we're not very good at that. For level 4, which Google are now pursuing because of the difficulty of the handoff problem, you really need a very high detection probability. And that could just take us a lot of time. What I advocate actually in the short term is let's try something I'll call it level 2.99 or a guardian angel system, where the human must pay attention all the time, but we have an autonomy system running in the background that will do its best to say, look, if the human is making a mistake or the situation is such that an accident is incredibly likely, can we jump in and take over to prevent an accident? And I think that could be a way to use the technology we have in the more near term to actually save lives. And obviously it's a tremendous societal problem, over 30,000 fatalities per year from driving, over 1 million worldwide, and there's a great need to address that. So that's the self-driving cars sort of some challenges. And now I want to try to talk a little bit about perspectives on mobile robot navigation. And in a neuroscience context, I thought I'd ask, and I'm sure you all know this, but who won the 2014 Nobel Prize in Medicine or Physiology? Anybody? Mosers, yeah, and O'Keefe. And so the 2014 Nobel Prize went to O'Keefe for place cells and the Mosers for grid cells. And I had the pleasure to be funded under an Office of Naval Research Multidisciplinary University Research Initiative with Boston University, Mike Hasselmo, who's another really top person in this area. And grid cells and place cells have been called the sort of GPS system of the brain, and a positioning system. I wouldn't call it a G, global positioning system, a L, local positioning. But amazingly, if you have a rat foraging in a sort of open field and recording over time, the Mosers discovered this periodicity in the neural firing patterns in the entorhinal cortex, which is sort of stunning. And then in the early 70s, O'Keefe had discovered place cells. And my understanding, and I'm not a nerd, is that these parts of the brain, the entorhinal cortex and the interaction with the hippocampus, have a really critical role in forming long-term memories. And if the hippocampus is lesioned, like the patient HM, the ability to form long-term memories is taken away. And myself, as a sort of navigation-obsessed person, is that I think where am I is one of the most fundamental questions in intelligence, that knowing where you are provides, in effect, an indexing mechanism for recall of information. Because just think of all the, I'd like to have Google for the physical world and have an indexing mechanism that combines space and time. And so, all right, so if, and so back when O'Keefe was discovering place cells, you know, robotics was just getting started. Someone like Hans Marvic.
It would be a very simple task. he hit a problem.
There were things that, although they at first looked like they might be easier because human beings do them more easily, that in fact turned out to be heartbreakingly difficult. And those were things like looking at the world and seeing what objects there were in front of the camera that was connected to the computer, and moving around competently in the world, you know, the typical robot tasks.
So this, Marvic was a real pioneer in the whole question of representation. How do you represent the world is really important to us as roboticists. And so my own sort of personal history, I worked on robot navigation in Oxford using sonars and trying to develop ways where you could predict observations, match them against representations, and then navigate. And so if so this problem of SLAM is how you generate a map from noisy local data and then concurrently estimate the position of the vehicle. And SLAM is sort of a cornerstone, I think, of autonomy and mobile vehicles. And the basic essence is that if your position estimate is drifting, say the odometry or dead reckoning shown in blue, by building a model and doing what we call loop closing, you can correct your error as you navigate through the world. And so SLAM is difficult because you have to think about how you represent the environment, you have to perform inference, and we have to build systems as roboticists that are autonomous in the world. And so if, and I think from a sort of neuroscience, like as an outsider looking in, if we can get at this representation issue, that to me is at the heart of it. You know, how is map information represented in the brain? And I feel like the grid cell place cell story is only a tiny little part of the story. So how are we doing on time, David? Do you want me to go longer since we had a little extra time from the starting, or should I? So I got 10 more minutes? Great, okay, just want to make sure, because, all right. So if I had to try to summarize over 25 years of thinking, gosh, almost 30 years of thinking about robot navigation and mapping, you know, this sort of, a lot of it comes down to doing inference and doing the inference in a sparse sort of representation. More recently, something we're excited about in robotics is building dense representations. And so has anyone heard of Connect Fusion, a way of using GPUs, so modern? I feel like we're all gamers now. We've got to take advantage of this massive parallelism. This is some work in collaboration with a guy named Tom Whelan in Ireland, who's now at Oculus Rift doing virtual reality. And it builds on Connect Fusion out of Microsoft Research, and I'll just give you a little example here. So the idea is using a GPU, you can build a truncated sign distance function representation, which is like an implicit surface volumetric representation. And Tom came up with this hack, really clever idea of taking Connect Fusion and periodically moving the volume in the world with a circular buffer trick. And the idea is that as new material enters the world, say from the left shown in blue, and old material sort of falls out of this volumetric model, you can do raycasting and triangulation efficiently on the GPU. And what we did working with Tom at MIT is to add what we call a pose graph. So the representation that's sort of dominant now in robotics is what we call pose graph optimization, where you maintain an estimate of the trajectory of the robot, and you use that to do inference to sort of combine data over time. And so here is just walking around at Tom's apartment in Ireland, and I'll show you an example here. Look at the quality of the models you can build. We can get sort of rich 3D information. And so the sort of things that we've done in my lab is taking the sort of pose graph optimization approaches, combining it with dense representations. And I'll just give you a little example. This is from about 8 minutes of walking in the Data Center at MIT across 2 different stories. And you see that loop closing problem I mentioned? There was this drift, those 2 blue chairs that I showed. Actually, I'll play it again to show you. So when you have drift and the model doesn't align, and this has to be something that biological systems do, is how do you create that sort of representational harmony, that like reinforcement versus, and so you have this error that accrues from just trying to do local tracking, this sort of path integration is the word I was looking for. There's a whole language that neuroscientists use that's different than what we use, but the path integration error has to be corrected. And so those 2 blue chairs were sort of aligned somewhat automatically, and you get to build this rich model that you can sort of fly through. Now, there's still a lot more work to be done, but I'd like to make a model of the entire MIT campus that you could sort of make as like a virtual aquarium. You could fill it with water and sort of swim through it. And so at the end of the day, you get a model like this. And that all runs in real time using mesh deformation techniques from graphics. So with my final time, I'm just going to talk a little bit about like a future vision for research. And to me, I want to go back like historical. So David Marr, people familiar with David Marr, I hope. He defined vision as the process of discovering from images what is present in the world and where it is. And I want to highlight the what and the where. And I think combining those two is really, I think, really powerful. I'd like to create a more object-based understanding of the world that facilitates lifelong learning. And let's build rich representations that leverage knowledge of your location to better understand about objects, and vice versa, knowing what you're looking at to better understand location. And so one example, I have a student, PhD student, Siddhi Pillai, working on what we call SLAM-supported object recognition. So I'm sure you're familiar with deep learning and all the ImageNet and all the process and image labeling. But a lot of that looks at just single still images off the ImageNet. And for computer vision researchers, it's alluring to think of what can be inferred from a single image, absent any other information. But as a roboticist, I care about agents that need to move intelligently through the world, interacting with the world, and adding back the context, adding the ecomotion. I think that can lead us to much greater robustness. So we had a paper in RSS in Italy last year. This is, I'll just show little bits from the video of this. And the idea is to take a SLAM system, so a monocular, single camera, what we call semi-dense mapping system, so it's not going to the full tilt of the Kinect Fusion. And this is a wonderful open source SLAM system out of Spain, something called OrbSLAM. From past collaborators of mine, have done some really wonderful work and made it available for free, open source. And this is data from Dieter Fox's group in Washington. And the idea is that there's been this tremendous progress in object recognition, and a lot of it comes to things like how do you hypothesize where to look, and how do you generate proposals. And then also, there's this whole conversation about feature encoding, or maybe with deep learning, you just ignore all that and it's a big black box. But in SLAM, these sort of semi-dense mapping is a way of getting some of the benefits of the denser representations, but still running in real time. And also some great work out of Imperial College, what's called SLAM++, or object-oriented SLAM. What we'd like to do is to get away from the raw pixels and build on top of that a true, more semantic, object-based understanding of the world. And just as like an illustration of the concept, if you run a SLAM system to help you better hypothesize where the objects are, you're going to do much better in terms of classifying the identity of objects. And if, let's see if we have this side by side here. So in essence, you sort of build a model and you're concurrently detecting objects. I'll just jump ahead and show like a little bit of, so in essence, the way it would work is, this is us comparing against single view recognition. The blue line is ours, and a key thing is that using much less computation, we can get better precision recall curves than a system that looks at single frames. And in some ways that should be obvious. If you use multiple frames, you should do better. But the hope is that this using the where information helps you do better with what. And ideally there's a sort of positive feedback reinforcement loop. And I'm going to try to switch back now to the biological story. And so one of my collaborators in the Muri grant is Howard Eichenbaum at Boston University. And I just grabbed one of his images, and I hope he wouldn't mind me doing this. But and he thinks a lot about the two different streams of information processing in the entorhinal cortex, the lateral versus the medial. And what's known as sort of the what stream and the where stream. And these sort of merge in the hippocampus. And the sort of things that he's doing in experiments with animals is to try to tease out the interactions between the sort of object detection, what, and the location estimation. And part of me feels there's got to be some general purpose machinery there that's getting reused in the different domains. So, and this Google for the physical world, that's a goal for me, is to have, think about deep learning object labeling as a sort of as a sensor, as a capability. It's not going to be perfect, but if we can couple that to location estimation, just imagine being able to use your smartphone and just have, what is where in the world. And then I think a big part of intelligence is retrieval. So if you think about Google, there's the crawling the world internet to gather information and build the index database, and then the ability to use the indexing mechanism, the PageRank, to quickly get an answer. And I feel in the brain, there's got to be something like that going on, where there's this sort of background process. Maybe I call it like robot dreaming, where overnight your day's journey is sort of somehow harnessed. But there's some indexing mechanism with location playing a part to rapidly recall information. So to conclude, my dream is to achieve persistent autonomy and lifelong map learning. Say a robot car that as it drove around Boston, it would get better and better. It would learn about the world. Can we robustly integrate motion? The mapping and localization I talked about is only part of the story. We need to close the loop and integrate it with planning and control. I think the question of robustness is really important. So for the SLAM systems I've worked on and others, we've made tremendous progress, but still we have algorithms where they often produce really good answers, but sometimes they produce garbage. And so how would a system know that it knows the answer, and can we make a sort of everything but the kitchen sink for representation where we pull in the geometry, the appearance, objects, semantics, text, labels, and just have like a whole plethora of representations that are all linked together. And ultimately, I think, even though this recent work in computer vision is very excited, if you think about trusting a car to drive your children to school, maybe 88% precision isn't good enough. We need to get to that perfection point of the ROC curve. So finally, some questions for like the neuroscience folks. If do biological representations support things like loop closing and not, even though we know where we are, like could you have like multiple location hypotheses? Is there some notion of an experience map that there's notion that, and this thing I call pose graph optimization, is there any biological mechanism for it for correcting path integration? I think there is in the grid cells. What are the grid cells really doing? Is it just path integration only? Is there path correction? And could there be this indexing mechanism there? So at that, I'll stop and take questions.
Hi.
Oh,
Yeah, it's here.
yeah. Oh, hi, thanks.
Hi. Yeah, this might be a very naive question, but the challenges you spoke about the self-driving car seems to be, one car driving in an unpredicted random world. But shouldn't we think about a world in which all the cars are self-driving and they can communicate with each other, so a lot of those problems go away, and maybe some other problems come into play?
That's a great point. So vehicle-to-vehicle communications, vehicle-to-infrastructure technologies, they really could make the issue of making left turns and so forth easier. One question is, like, how do we get there from here? If sort of partial penetration, and also whose job is it? If it's the government's job, then it might take a while, But if I love the government, sorry. And but Google's approach is the idea it should all be in the car. Like the car can do everything, and so it'll be interesting to see how that evolves.
Driving in this quietly random world is very difficult, but driving on a highway, let's say, for hours through Kansas can be easy from this point of view. I wonder what you thought about this.
So, well, I think that Tesla's autopilot is amazing in how well it works on highways. I mean, I've just been, I crawl the internet for YouTube videos, and I'm just really impressed with the performance, sometimes at night, sometimes in rain. So highway drive, Google had a really sophisticated capability for highway driving about 3 years ago. They did an employee trial with 140 employees, and their system was so good that the people trusted it so much that they could have over-trusted it. And so I think we sort of have highways now. It's just it's 1 minus epsilon, and what is epsilon, and can the human deal with the epsilon?
Can you share your thoughts about liability when we get to level 4 autonomy and what that implies for people and for regulation?
Right. I think just speaking personally, just an MIT professor, I think it's a really difficult question. And I don't know the answer, but I wonder if we might look at vaccines as an analogy. I've been told that vaccines are the greatest medical advance of the last century. And could you imagine a world in which we could achieve a 100-fold reduction in accidents, but there were sort of tragic, small number of cases. If somehow society could bind together like it did with vaccine technology to create some sort of fund or some sort of collective thing that it's as a society we made a decision we're going to take this traffic fatality problem on, and not single out individual, people if something happens. But I think that's a big question for policy debate going forward. Yeah, one more, please.
Will you talk about affordability and how this evolves from a science project to something that's practical and useful?
Well, I think the question is about affordability. It's amazing. I was just at the Consumer Electronics Show a few weeks ago, and Google has created this tsunami wave of interest from the OEMs, from the car manufacturers and their tier 1 suppliers and their suppliers. And if the quantity is high enough, the costs can drop. So I think actually that's been one of the great things. For example, LiDARs that were $75,000 could be a lot cheaper. And what if there was a LiDAR in every car? That might actually make a dent in traffic statistics. Okay.
Just as a follow-up.
Yeah, follow up.
As a follow-up to that, how many factors of 10? How many factors of 10 does the cost have to drop before this really is going to be useful?
Well, if we used the Velodyne LiDAR as an example at $75,000, last year at a public workshop, their founder forecast that they could be a few $100 if he could make 1 million of them. So I think, at least 2 factors of 10 are possible if the quantities come. But that, I'm on the more conservative side that it's going to take longer that for the whole thing to happen. But if we can actually reduce accidents, then we'll be making a difference, and I think there'll be some momentum.
Thanks, John, again.
Thank you.